So, have you ever stopped to think about how scientists count things that are literally impossible to see? I'm talking about the atoms in, say, a piece of metal. It feels like it should be impossible, like some kind of magic trick. But the solution, well, it actually starts with a really simple idea. Okay, so to get our heads around how chemists count the uncountable, let's start with a much more down-to-earth problem. Just imagine I handed you this massive bag of rice and asked you one simple question.
I mean, seriously, how would you do it? You're not going to sit there and count them one by one by one. That would take forever. There's got to be a better way, right? A clever shortcut. And you know what? This is exactly the kind of problem scientists just love to sink their teeth into.
And that clever workaround, it's a technique called counting by weighing. It's brilliant. Instead of counting all those little grains of rice, we're going to let their weight do all the heavy lifting for us. It's a really elegant and simple process when you break it down.
Okay, so here's how it works. Step 1, you grab a small, manageable sample that you can actually count. Let's say 20 beans. You weigh just those 20. Step 2, you use that weight to figure out the average mass of a single bean. Easy enough. Now, once you have that magic number, you move on to step 3. You weigh the entire giant pile. And for the grand finale, you just divide that huge total mass by the average mass of one bean. And boom, you've counted the whole pile without having to count a single extra bean. So let's look at some real numbers here. Our little sample of 20 navy beans, it weighed 3.72 grams. You do a little quick division, and that gives us an average mass of 0.186 grams for each bean. Now look, is it perfect? Of course not. Some beans are a little chunkier, some are a little smaller. But for counting a gigantic pile, that average, it's more than good enough. It's incredibly powerful.
So the big takeaway here is this. The scale basically becomes your counter. That average mass we calculated, that's the key. It's what lets you count enormous quantities super fast and efficiently. And this simple idea, this is about to take us from the kitchen pantry straight into the world of chemistry.
Because, believe it or not, chemists face this exact same problem. You can't just pick up an atom and put it on a pile, right? They're impossibly small, and there are just a mind-boggling number of them. So what did they do? Well, they pretty much stole the exact same idea we just used for our beans.
And the connection here is, well, it's a perfect one-to-one comparison. Our beans are too numerous to count one by one. Atoms, they're way too tiny and numerous to count. But the solution is the same. You can count both of them just by weighing them. The average mass of our bean has a direct counterpart in chemistry, and it's called the atomic mass of an element.
You know, this whole concept is so important, so fundamental to chemistry that it gets its very own special unit of measurement, and it's called the mole.
I mean, think about it. We do this all the time. We have easy words for quantities, right? We buy eggs by the dozen. That's 12. We buy paper by the ream. That's 500 sheets. Well, chemists needed their own version for atoms. They needed a standard unit, like a chemist's dozen, that stood for a specific and frankly enormous number of particles.
And wow, that number is just staggering. 1 mole of anything, whether it's atoms, molecules, you name it, is 6.02 times 10 to the 23rd power. Let me try to put that in perspective. That's a 602 with 21 zeros after it. It's a number so big it's almost impossible to wrap your head around. But that is the number for counting in chemistry. And it has a famous name, Avogadro's number.
So really, don't let the name or the giant number intimidate you. A mole is just a word for a number, exactly like dozen is a word for 12. But what makes this specific number so special is that it's the perfect bridge. It connects the tiny, invisible world of atoms to the world we live in, the world of things we can actually see and weigh on a scale in a lab.
Okay, and here's the final piece of the puzzle that brings it all together, molar mass. This is the critical link. The molar mass is simply the weight in grams of exactly 1 mole of something. So, for example, if you go into a lab and you weigh out exactly 26.98 grams of aluminum, you know for a fact that you are holding 1 mole of aluminum atoms. You know with absolute certainty that you have 6.02 times 10 to the 23rd atoms right there in your hand. And you didn't have to count a single.
And this is way more than just some neat little math trick. Being able to count atoms just by weighing them, that is the absolute foundation, the bedrock of all modern chemistry. It is literally how we build the world around us with incredible precision.
So let's do it. Let's take a real-world example, like a piece of aluminum wire. It's a super simple 3-step process. First, you just put the wire on a scale and get its mass. Second, you divide that mass by aluminum's molar mass to find out how many moles you're holding. And finally, you multiply that number of moles by Avogadro's huge number, and just like that, you know the exact number of atoms. It's really that straightforward.
So why does any of this matter? Well, it's everything, really. Think about it. Chemical reactions are like recipes, and they depend on having the exact right ratio of atoms. By using the mole to count them, scientists can mix and match elements with unbelievable precision. And that's how we get everything from life-saving medicines to super strong new materials to the complex little microchips that power our entire digital world.
So it kind of leaves you with this one big thought, doesn't it? This one simple idea, counting by weighing, unlocked our ability to control the very building blocks of matter with total confidence. It has completely transformed our world. And it really makes you wonder, what are the limits now? If we can count atoms, what can't we build?